In this lesson, we are going to learn how to calculate the present value and the future value of an investment. Now, the first major concept that we need to understand before we start any examples is talking about the rate of the stream of money. And that means how much money is coming in per month or per year, per week, per time frame. And so when we think about a flow of income, you're just looking at it as some kind of continuous stream of money. And sometimes it's possible to estimate the rate of flow of the stream with the function. And when we do this, the function is called the rate of flow function. And then when we integrate that rate of flow function over a specific interval, we would find the total accumulation of the stream of money over a specific time frame. The first example we're going to be looking at is the accumulated value of a non-interest earning stream. So if you have a stream of money coming in and it's not earning interest, then what you want to do is just find that rate of flow function and integrate it over the interval that you're interested in. So now in example 1, we are going to practice using the formula we just went over. And that formula will help us determine the amount of money that we've collected and accumulated, but without interest. So we're literally just counting how much money we have set aside over a certain amount of time. So the question says, revenue flows continuously into a retail operation at the constant rate of F of T is equal to $128,000 per year. As the money is received, it is placed into a non-interest earning account. We need to determine how much money has accumulated in the operations account at the end of a 3-year period. So using the formula we just looked at, we want to integrate that rate of the money flow, and we want to do that from 0 to 3 because we need to count up how much money we've saved in a 3-year period. So this is specifically for just counting up the money that we put aside, not including interest. So when we integrate, we have 128,000 times t, that's our antiderivative, and then we evaluate it from t is equal to 0 to t is equal to 3. And we have $384,000. So at the end of 3 years, after we have put in $128,000 every year for 3 years, we get $384,000. Now we're going to look at an example where we put money in an interest-bearing account. However, we don't have a continuous flow of money. We are just dropping in one lump sum as an initial deposit, and then we're stepping away from it and just trying to let it grow based on interest. So the question says, if a one-time lump sum investment of P equals $128,000 is made into an account paying 7% interest compounded continuously, the amount A of the money that will have accumulated at the end of 3 years is. So we have to find what we get at the end of 3 years. So this P represents the principal. It's what you initially deposit. In this case, we're just putting in one lump sum and then just letting it grow. This could also be called the present value. That means what we're presently depositing, and then what we get out later after the 3 years, then we'll look at that as the future value. What are we going to have in the future after 3 years? So when we talk about continuously compounded, we're going to use this formula here where we have A is equal to P times E to the power of R times T. So this A is equal to the accumulated amount. So that's going to be the amount that we have in 3 years. That's going to be basically our future value. R is going to be the rate of interest, but it's going to be in decimal format. So in our case, the 7%, we would input that into the R as 0.07. T is the time, and then P is our principal. This E here is our natural constant. So when we put all of our information into this formula, our present value or our principal is 128,000 times the natural constant raised to the power of our interest rate, which is 0.07, times the number of years that have passed, which is 3. When we calculate that, we're going to get approximately $157,910.79. So this is how you would interpret it. When we deposit that $128,000 into an account with continuously compounding at a rate of 7% at the end of the 3 years, this $157,910.79 is what we're going to have as our future value. Now let's talk about annuities. And an annuity is when you're making regular payments of the same amount at the end of consecutive periods. So that's like your pay period. And that's going to go over a fixed length of time. So, for example, I want to add $100 into an account every month for 2 years. So that 100 is my fixed payment. And then if I'm doing that for 2 years monthly, then I have 24 pay periods. So I'm going to do that 24 times. And you can do it however you want, whatever time frame you want. You can do it monthly, you can do it quarterly, you can do it annually, but it's just like a regular payment into an account that earns interest. And then this formula below finds the future value for that. So it adds up the money that you put in for each pay period and adds it all up. So the N for the upper limit of your integration, that's the number of pay periods. So in my example, that would be 24. If I'm doing it monthly for 2 years, I would have 24 pay periods. The P represents that fixed amount that I keep adding into the account. And the R, of course, is your interest rate, but in decimal format. And T is the time frame. Now, looking at example 3, we have, suppose that at the end of each month, $100 is put into an account paying 6% annual interest, compounded continuously. And we want to find how much money we would have at the end of 6 months and then after 20 years. So a couple things I want to point out, the keywords that you should pay attention to. It says that the deposits are being made at the end of each month. That means each pay period is a month. And it says $100 is put into the account every month. So because it's not one lump sum where you're just putting in one deposit and then you're stepping away and letting the interest help it grow, you are making multiple payments. If it was just one lump sum, you would use A equals P times E to the power of R times T. When you're doing an annuity where you're making multiple payments, then you want to integrate. So you're accumulating all the values for all the pay periods. So with annuities, you want to evaluate an integral using that same continuous compounding formula. So if we're looking at pay periods that are each month, and we're looking at over a period of 6 months, that means we have 6 pay periods. So when we set up our limits of integration, we're going to set it up so that our lower limit is 0 and our upper limit is 6. This is over 6 months. And of course, here's our deposits each month. And then here is our interest rate as a decimal. So I have to evaluate this. When we evaluate this and we find the antiderivative, we get that we have 20,000 e to the power of 0.06t, and then we want to evaluate that from 0 to 6, and when we do that, we get approximately 609. And these are just approximate values. If you actually took the time to add up each individual month, you'll see that it'll be a little bit off, but this is a good estimate. So what this means is after 6 months of putting in $100 into an account each month, and the interest earned is 0.06 per year, you would have, after 6 months, $609 approximately. Now let's look at the 20-year period. Since our pay period is in months, and the question is asking us to figure out how much we're going to have at the end of 20 years, the units are not the same. You want to make sure that your limits of integration, the number of pay periods, is going to be the same as the Unix that's given in the question. So we want to make sure we change 20 years into months. So if I take 20 times 12, that will give me 240 months. So just pay attention to that. So when we set up our integral, we're going to go from 0 to 240. And again, that's because we had to change 20 years into months. And we're going to integrate that same function, which means we're going to get the same antiderivative. However, instead of going from 0 to 6 pay periods, we're going from 0, oops, I forgot my 0 there. We're going from 0 to 240. And at the end of the 240 months, in that account, you should have approximately $46,402.34. Make sure in your notes you put that 0 on the end there. It should be 240. In example 4, we're going to solve for present value. Everything that we have looked at so far has been trying to find the future value. Now we're going to look to see how to solve the present value. So remember, the present value is what you have to invest right now in the present, and then what you want to have in the future at the end of your time frame. That's your future value. So since we're only investing a lump sum, it doesn't say anything about making regular payments of a certain amount of money, then we don't have to worry about integrating. We just use the A equals P times E to the RT. That's our compounding, our continuously compounding formula. But because it's asking for our present value or the principal, we need to solve for P. So you could either put all those values in now and then solve for P, or you could just rearrange the equation for P. It doesn't matter how you do it, it's just your preference. So the A, remember, is our accumulated value or our accumulated balance. That's going to be what we have later. So the A is going to be our 15,000. Time is 10 years. So if you solve for P first, you can write it as A over e to the power of RT, because you would have to divide both sides of the equation by e to the power of RT. And another way that you can write it, and this is what the book uses, instead of having the e to the RT in the denominator, it gets flipped up with a negative exponent. So you could use this as well. So I would plug in 15,000 for my accumulated balance, and then I would put in 0.08 for my interest and for R, and then multiply by 10 years, and what we would get is $6,739.93. So this means if I invest $6,739.93 right now, and 10 years in an account that has 8% interest, we would have $15,000. So the previous topic and the formula that we talked about was regarding an annuity where there were fixed payments made over a number of payment periods of equal time. But now we're going to look at the case where we're not making fixed payments at specific times, but rather we're making the assumption that the money coming in is a steady stream rather than a specific amount at specific times. So we're going to assume that that money just flows in. And in this formula, the capital T represents, that's this right here, the capital T represents the entire time frame in which we're collecting this money. And then the little t right here, that is the time from 0 to when the deposit is made. So we have individual deposits that go into this account, but we're looking at one specific deposit to give you an idea of what's going on. So here's our rate function, and the entire time interval is from 0 to capital T. And we are going to make the assumption that, and I called it D for deposit, that we just get a deposit here at this time, and we're calling that time T. So from 0 up to when we make that deposit is time T. Now, from the time that that deposit is put into the account, we have to make sure that we're counting the interest from that time on. So we want to find the interest from whatever the capital T is minus the time that it missed from 0 to T. And then anything after that is where we're going to calculate the interest for that deposit. So this formula for the future value is a simplified version of something else, and I'm going to walk you through it so that you understand where this comes from. Let's see. So if I go from 0 to capital T over that whole time frame, we want to take the rate function and we want to multiply it by the deposit and all the interest so that we have e to the power of r. Now normally we have rt here, but because we're looking at it from the little t up to the big T, we're going to write the time as capital T minus little t. And then of course we have our dt. Now this looks a little bit different than this. This is still good, but what the author of this book did, he used exponent rules to break this up into pieces. So thinking back to our exponent rules, when we multiply bases that are the same, we add our exponents. So that means if I break this e to the power of r times capital T minus lowercase t, let me make this as a separate. So that would give us e to the r capital T times e, let me erase that, times e to the minus r lowercase t. So we just split this up into two factors with base e. And then what the author did is, because this integral is not dependent on t as far as the variable is concerned, we can pull this out in front. That's where this is coming from, this e to the power of r capital T. And because little t is our independent variable, we needed to leave that in there. So this is where they're getting that formula from. And then if you want to solve for present value in the case that you have this steady flow and not at specific time frames where you're depositing money, here's the present value formula for that steady flow of income. The last question of this lesson, we have that a company can buy a machine that is expected to increase the company's net income by $10,000 each year for the 5-year lifespan of the machine. The company also estimates that for the next 5 years, when they invest that money, they'll get 7% compounded continuously. So we need to find and interpret the present value and the future value of this income stream. So here's our present value formula. The capital T is the amount of time over that entire time interval. So that's going to be a 5-year time span. So we're going to put in, for the capital T, we're going to put in 5. This F of T represents the rate of the money flow. And since we are told that this is $10,000 each year, that's our rate. So I'm going to put $10,000 in for this F of T. And then for this R right here, we need to put in our interest rate in terms of a decimal. So that would give us 0.07 in for that R. Now when we plug everything in, this is what it's going to look like. And then we have to find the antiderivative and evaluate it from 0 to 5. So think back about your substitution. If you let u be equal to negative 0.07t and you do a substitution, then what you're going to get is 10,000 over negative 0.07 times e to the power of negative 0.07 times t. And then when we evaluate that from 0 to 5, we get approximately $42,187.42. So for the future value, we have a slightly different formula, but it's all the same values that we're going to plug in. So for the big T, I'm plugging in 5, so that's 5 here and 5 here. Our rate of flow is still 10,000, and then our interest rate is 0.07. So when we evaluate that, this value in front of the integral just comes down, and we're going to multiply it by the antiderivative, which is 10,000 over negative 0.07 times e to the power of negative 0.07t, and then we're going to evaluate that from 0 to 5. So what this gives us is $59,866.79. Now, what does this all mean? The future value is telling us if we put that $10,000 that we get each year and we invest it immediately, then at the end of that 5 years, we're going to have $59,866.79. This present value here is telling us rather than putting in the money regularly and put it over that time span each year, if we put in a lump sum at the beginning and we still want to get $59,866.79, but if we put it in as a lump sum, all we would need is $42,187.42. And that is because if we invest $10,000 one year and then $10,000 the next year, that second $10,000 isn't going to earn the interest from the first year. It's going to just go from the second year and on. And then when we put in the $10,000 from the third year, it's only going to earn interest from the third year and on. Whereas if we deposit it as a lump sum at the beginning of that time frame, then all of that money will earn the same amount. We'll get that interest over the entire time frame, which means we don't need as much because we'll gain more interest. So this would be our lump sum if we did that, our $42,187.42. So for our lesson summary, we went over a lot of formulas, so I just want to go through and list everything that we talked about with the formulas next to it. So for the accumulated value, when you're not putting it into an account that earns interest, if you just want to add up the total amount of money that you or the company puts in without interest, then we want to use this formula. And we would go from 0 to capital T, whatever that time frame is, and then we would enter in here the rate of the flow of the money that you're putting into this account. Now, if you want to find the future value, what you're going to have at the end of a certain time frame, if you're only putting in one lump sum, if you just put in a lump sum at the beginning and walk away from it and let it grow, then you want to use this formula right here. So A is your accumulated amount or your future value. P is your principal or the initial lump sum. And then of course your R is the interest rate and the T is the time. If you're looking for a future value of an annuity, that's where you're not putting in a lump sum. You're putting in regular payments of the same amount over and over again. You're going to use this formula here where you're going from Z to N, and this little n represents the number of pay periods, the number of times you're depositing this certain amount that's fixed. Now, if you want to find the present value of the annuity, so that would be working backwards. If you want to figure out how much you need to invest now to have a certain amount later, you're going to use this formula right here. And that's specifically for an annuity. And then down to the last two topics that we talked about, which is the future value when you're talking about an income stream and the present value of when you're talking about an interest earning income stream. That's a mouthful. So these are your formulas for future value when you're dealing with an income stream, and then present value for an income stream. And then all the variables represent the same thing. Capital T is over the entire time frame. Your F of T is your rate of flow, and your R is your interest rate in decimal format.